When you are creating a model and want the results to match that of some reference or measured data, you can do so by approximating some of the input values in your simulation. In COMSOL Multiphysics, you can do this by performing a parameter estimation study. The parameter estimation study step enables you to estimate the value of a parameter or set of parameters so that your simulation results match your experimental results. This functionality provides a simplified interface through which you can quickly formulate, set up, and solve a least squares problem based on time-dependent measurements entered through either an interpolation function or user-defined reference expression. Use cases for this functionality include curve fitting, parameter estimation in partial differential equations, and other inverse modeling problems. In this video, we will show you how to conduct a parameter estimation study. Please note that this study step is only available for time-dependent models, needs some set of reference data for problem formulation, and requires the optimization module for use. Here we have a modified version of the elbow bracket tutorial model opened up, and in this tutorial, we'll be performing a time-dependent heat transfer analysis on this model. In the parameters table, you can see we've created several parameters that help define the physics, as well as the material used in this simulation. First, we have the parameter Tamp, which is for the temperature amplitude, and this is used in the temperature boundary condition in this expression. So this expression enables us to apply a sinusoidal temperature variation on this boundary. If we wanted to see a graphical display of this temperature variation over time, we could copy this expression, paste it into an analytic function of which we've already set up, and then specify an increment of time which we want to see the temperature variation for. Here we have it going over the course of a day, so from 0 seconds to 86,400 seconds. So we can click plot, and here we can see the temperature variation over the course of a day that we are subjecting our elbow bracket to on this boundary. Next, we have the parameter HTC for the heat transfer coefficient, and this is used in our heat flux boundary condition. So here we are prescribing some convective cooling on this boundary on the right end of the elbow bracket. Lastly, we have the parameters rho and Cp, defining the density and heat capacity, respectively, and these are both used in the solid 1 node, again, under the settings for density and heat capacity. Under thermal conductivity, you'll notice the property value is set to be taken from material, but we have not added any materials to our component. So currently, this property is undefined. We will leave it at this setting for now, for reasons that will become clear in just a few moments. As I mentioned earlier, we'll be performing a time-dependent analysis, and thus, we have added a time-dependent study step, and we want to compute the temperature distribution in the bracket over the course of a day, so we are going from 0 seconds to 86,400 seconds, and computing the temperature every 600 seconds or 10 minutes. Speaking of time, in the interest of time with respect to solving our model, we will use an extremely coarse mesh and build that so that our model does not take as much time to solve. So for this simulation, we are particularly interested in the results we get for the temperature on this boundary on the right end of the elbow bracket. And we want to compare the results we get here with this set of experimental data from an external file. So here in the first column, we have time, And in the second column, we have the temperature measurements. And we want to minimize the difference between this set of temperature measurements and the results we get for the average temperature on this boundary. To do this, we can formulate this as a least squares problem, where we want to minimize the deviation between what the model computes is the average temperature on this surface and the actual measured data. So this is an inverse modeling problem, and what we'll want to do is estimate the value of K, thermal conductivity, so that our simulated data best matches our reference data. So to start setting up our problem, first we'll want to create a global parameter for the thermal conductivity. So we can go in our parameters table, let's call this parameter K. We can enter a rough estimate of the value, so we'll enter 0.1 watts per meter Kelvin. And then enter thermal conductivity for the description. Now we can return back to the SOLID1 node and update that setting to user-defined and enter K. Next, we'll want to incorporate the experimental data for comparison. We can do this by using a function, an interpolation function. Here we can enter the data in manually, or we could use the Load from File button, navigate to the folder in which the file is contained, change the file format so it can be selected. In this case, we are working with a .csv file. Select the file, open it, and here you can see that data was entered in automatically. In the first column, I have the increments of time, and in the second column, I have the temperature measurements. So we'll want to update the units for those. Seconds for time, so we enter S, and then for temperature, we will enter K for Kelvin. Now we can go ahead and click Plot to obtain a preview of that function. You'll notice that I didn't change the settings for interpolation or extrapolation, and this is because the parameter estimation study evaluates the difference between the model and reference data only in the times specified by the argument column of our function. Thus, the interpolation setting is not important, since our data points where the times and temperatures are explicitly stated are the ones that are used for comparison. Additionally, the extrapolation setting does not matter either, since we are only looking at a fixed interval of time. So, as mentioned before, we want to obtain the temperature on the boundary on the right end of this elbow bracket. To do this, we can go under the Definitions tab, under Component Couplings, and select the average coupling operator. This coupling operator computes the average of an expression over the geometry you select. Since we want to obtain a quantity on this boundary on the right end, we change the geometric entity level to boundary, and then can go ahead and select that surface. To obtain the average quantity for this source geometry, we can go ahead and create a local variable and call it TAV for the average boundary temperature. And in the expression, we can call out our average coupling operator by writing av op1 and then using parentheses, and here specifying the quantity we want to calculate the average for, which in this case is temperature. So we enter T, close the parentheses, and you'll notice that the unit automatically updated to Kelvin, and we can fill in the description, average boundary temperature. So this is our model expression, which will be used in comparison to the experimental results. Alright, so now that we've set that all up, we can go under the Study tab and click the Parameter Estimation button to add that study. In the Settings window here, we are provided with a simplified interface which we can use to quickly set up a least squares problem. Under the Study Step setting, you can see our time-dependent study step was selected by default, which we can confirm if we click the Go to Source button, and we're brought back to that study step. Likewise, with the reference data used, we can see the interpolation function we defined earlier is selected by default, and if we again click the Go to Source button, we are brought to that previously defined function. Note that you can also choose the user-defined option to enter an arbitrary expression, usually dependent on t, the time. Under the model expression, this is where we are going to enter the variable we defined earlier, tav. And what I can do is use auto-completion by pressing the Control button and then the space bar, and then go under Component 1, Definitions, Variables, and then select comp1.tav. Notice that we specified where our variable was defined within Component 1 and did not simply enter tav. This is necessary because the parameter estimation study step works on a global level, and it will not see variables defined locally in a component unless you explicitly specify the scope of the variable, such as in this case, including comp1. Under the parameters section, we can go ahead and add the parameter that we want to estimate, which would be K thermal conductivity. We will leave the initial value set to our rough estimate, and leave the scale set to its default value of 1. Please note that this is an important setting that you want to make sure to define. The default value works for our problem here. However, you should make sure to specify appropriate scales for your control variables. For the lower bound, let's enter 0.1, and then for the upper bound, enter 3. Under the parameter estimation method section, we need to select the algorithm which will be used for our study. Under the parameter estimation method section, we have 3 options for the optimization algorithm we choose to use for computing the model. The first option, boundary optimization by quadratic approximation, is default and provides a derivative-free optimization algorithm. It is useful when the parameters to estimate control the geometry or mesh, which is not the case for our model, so we will not use this method. Next, we have the Levenberg-Marquardt method, which is a gradient-based optimization algorithm specifically designed to solve least squares type objective functions. For this method, constraints are not supported. Since we want to provide a lower and upper bound for our parameter estimation, we will also not use this method. Lastly, we have the SNOPT optimization algorithm, which is also a gradient-based method, and finds the optimal solutions to a very general class of optimization problems. With this method, any constraints can be applied. So let's go ahead and choose this method. And for more information on these methods, please see the chapters on optimization algorithms and optimization solvers in the Introduction to Optimization module documentation. Lastly, we have the Results While Solving section, and you can use this section to set up and display a plot group ahead of time to see the results while solving. If we toggle on the plot option, you can see default is the current setting, and this is with respect to any physics you have included in your model. So since we have heat transfer, we will obtain a plot of the temperature. Now that we are finished with the setup, we have a least squares objective function of the deviation between what the model computes is the temperature on the surface and the actual measured temperature data from our interpolation function. So we can go ahead and compute the model. Now that the model has finished solving, you can see we have a plot of the temperature at several times, and we can quickly plot that and toggle between those different time increments. So at this point, we need to do a bit of post-processing so we can more clearly see the comparison between our simulated results and the experimental data. To do this, we can go under the Results tab and add a 1D plot group. Under this plot group, we can go ahead and add a global plot. And this will be a plot of our computational results, so let's label it appropriately. For the expression, we'll want to use the variable we defined earlier, tav. So we can once again use auto-completion by pressing the Control button and then the spacebar, and we can go ahead and select tav. And if we click plot, you can see we have a plot of the average temperature on that boundary of the elbow bracket over the course of a day. Let's go ahead and make a few more changes. Remove the title, and returning back to the plot group node, enter a more appropriate label for the y-axis. And now we can add a second global plot, this time for our experimental data. So once again, we'll update the label for that. Under the expression, we can once again use auto-completion, and under definitions, functions, select the interpolation function. And let's change the description to experimental data. Once again, let's remove the title and change the appearance so it varies from our computational results. We'll change the line to none, change the color to red, and use markers. Let's use asterisk markers, and let's update the plot to see it. So in this plot, we only want to place markers for the reference data in the times that are specified in our argument column. You can see that the temperature was measured every 3,600 seconds, up to 86,400 seconds. So what we can do is we can go back into our experimental data global plot, change the data set to study 1 solution 1, change the time selection to interpolated, and enter that range. So we go from 0 seconds to 86,400 seconds with a step size of 3,600 seconds. And then go back under coloring and style and change the positioning to in data points. And you can see we have a plot with the markers placed in the times specified from our experimental data in the interpolation function. And you can see the data closely matches that of what our model computed. Now, we can obtain the optimal value of the parameter estimated k from these results. Under the Results tab, we can click Global Evaluation, and in the Settings window, change the time selection to the last time step. For the expression, enter our parameter k, and then click Evaluate, and we can see the elbow bracket made from a material with a thermal conductivity of 0.27 watts per meter Kelvin provides us with simulated results that match our experimental results. The parameter estimation study step simplifies the process of setting up and solving a least squares optimization problem. A general procedure for this process is as follows. First, we define parameters for the input values of our model. Next, we include the reference data in our model using an interpolation function or user-defined reference expression. Then, we define a variable to obtain the output quantity, which will be compared to the measured output data. After that, we add parameter estimation to our study and solve the model. Lastly, we post-process the results to compare our computed data to the reference data and obtain the estimated parameter value that provides the closest match between the two. To see a detailed introduction and demonstration in the full-featured optimization interface, please refer to our webinar on using the optimization module for parameter estimation in COMSOL Multiphysics.